Hello everyone, welcome to the channel Learn Math with Shobita. Today I am back with some collection of questions from linear algebra. First question, let V be a finite dimensional vector space and S, T from V to V be linear maps. Then option A, rank of S composition of T greater than or equal to maximum of rank of S, rank of T. Option B, rank of S composition of T equal to rank of S plus rank of T. Option C, rank S composition T equal to rank S into rank T. Rank of S composition of T is less than or equal to minimum of rank of S, rank of T. Okay, here we have the result rank of S composition of T is less than or equal to minimum of rank of S, rank of T. So option D is the correct one. Next question, let Aij be a let Aij be 10 by 10 matrix. Aij are real numbers for ij 1 to 10. Aij equal to minus Aj for all I, j, and ai, 10 minus I equal to 0 for all I. Then dimension of V equal to 40, 41, 44, 45. So how we can evaluate? Let us see. Given Aj equal to minus Aj, Aij equal to minus Aji for all I and j. So we have, this is a symmetric matrix. Aij equal to minus Aji for all ij means the given matrix is a skew-symmetric matrix. Also given Ai 10 minus I equal to 0 for all I. So this indicates therefore A19, A28, A37, A46, A55, A64, A73, A22, A91, which is all these entries are 0. Here A55 is a diagonal entry. For a skew n by n skew symmetric matrix, all diagonal entries are 0. So this is already 0. And A19 is equal to A91, A28 equal to A82, A37 equal to A73, A46 equal to A64. Since this minus of that, okay. So dimension of space of all n cross n skew symmetric matrices is given by n into n minus 1 by 2. Okay, we know that. Here n equal to 10. So putting n equal to 10, we get total 45 entries. Out of 45 entries, already this diagonal entries we have removed, so no need of taking in account. Remaining 1, 2, 3, 4, 5, 6, 7, 8. Remaining 8 entries, we count only 4 entries because Aj equal to minus Aij for a skew symmetric matrix. So we have to remove only 4 entries from 45 entries. So out of 45 entries, we have to remove 4 entries. Therefore, dimension is 41. Next question. A be a 2 by 2 matrix with real entries with determinant of A equal to 1 and trace of A equal to 3. Then what is the value of trace of A square? Okay. This is using properties of eigenvalues. We know that product of eigenvalues is the determinant and sum of eigenvalues is equal to trace. So lambda 1, lambda 2 be the eigenvalues of A. Then lambda 1 into lambda 2 you will get 1. Its trace is 3. That is lambda 1 plus lambda 2 is 3. Then if lambda 1, lambda 2 are eigenvalues of A, then lambda 1 square, lambda 2 square are the eigenvalues of A square. So trace of A square equal to lambda 1 square plus lambda 2 square. Now squaring both sides, squaring lambda 1 plus lambda 2 whole square, I get this. So after the calculation, I got trace of A square is equal to 7. I am not explaining all these things. Please pause the video and see the calculation. Next question. A, B and C be non-singular n cross n matrices such that AB equal to CA. So they have given AB is equal to CA and A, B, C are non-singular matrices. So since non-singular matrix means A inverse, B inverse, C inverse exist. So I will multiply A inverse on the right. So what you will get, A inverse into A into B equal to A inverse CA. So B is equal to A inverse into CA. Now determinant of B. Determinant of B will be is equal to determinant of A inverse CA. So this is equal to using determinant of AB equal to determinant of B into determinant of A. Using the properties of determinant, this can be written as determinant of A inverse into determinant of C into determinant of A. Okay. Determinant of A is inverse is 1 by determinant of A into determinant of C into determinant of A. So this gets cancelled. So we have determinant of B is equal to determinant of C. So in the out of 4 options, determinant of B equal to determinant of C is the B option. So option B is correct. Also we can verify trace B equal to trace C. We have B equal to A inverse CA. So trace of B will be equal to trace of A inverse CA. Okay, trace of AB equal to trace of BA. So this can be, if I take this is A and this is B, trace of AB is trace of BA. So this will be trace of CA inverse. So this is trace of C. So trace of B equal to trace C. Trace B equal to trace determinant of determinant C. So option B is the correct one. Next question. Let t from R2 to R2 be defined by t of xy is equal to x plus y comma x minus y. Then the minimal polynomial of t is. Okay. So let us find the matrix of t. We know that for R2, 1, 0 and 0, 1 is the standard basis. So t of 1, 0, we get to the calculation 1, comma 1. So this can be written as 1 into 1, 0 plus 1 of 0, 1. T of 0, 1 is 1 minus 1. We get after putting the values here. This can be written as linear combination of basis vectors e1, e2. So 1 into 1, 0 plus minus 1 into 0, 1. So matrix of T will be 1, 1, 1 minus 1. This is the A. Here trace of A is 0. Determinant A is, if you calculate, minus 1 into 1, 1 minus 2 minus 1, minus 1, minus 2. Determinant A is minus 2. Characteristic polynomial of 2 by 2 matrix is given by t square minus trace A plus determinant of A. So t square minus 2. This can be factorized into t plus root 2 into t minus root 2. So t plus root 2, if you put here instead of t, if you put a plus root 2i, this is not equal to 0. A minus root 2i also not equal to 0. Therefore, the minimal polynomial will be its characteristic polynomial, that is x square minus 2. So option A is the correct one. Next question. V is the functions from minus 1, 1 to r. V1 is the set of all functions satisfying f of minus x equal to f of x, and V2 is the set of all functions satisfying f of minus x equal to minus of f of x. Then what will be the options? Here V1 is set of all even functions, V2 is set of all odd functions, then V1 intersection V2 is 0 and V equal to V1 plus V2. Therefore, V is the direct sum of V1 and V2, that is V1 direct sum V2, hence option A is correct. Next question. If P is an orthogonal matrix, which one of the following is not true? Option A, P transpose is orthogonal, P inverse is orthogonal, P square is orthogonal, 2P is orthogonal. Given P is an orthogonal matrix, then P into P transpose equal to P transpose into P is equal to identity. Okay, so from this we can write P transpose of transpose into P transpose. This is equal to P transpose into P transpose of transpose is equal to I transpose, which is nothing but I. Okay, so we got P transpose is orthogonal. Also Since P is orthogonal, we must have P transpose equal to P inverse. Since P transpose is orthogonal, therefore P inverse is also orthogonal. Okay. So these two statements are true. We have to check which is the false statement. Now let us check about P square transpose. P square transpose into P square. So this you will get P into P transpose into PP. So this is P transpose into P. So if you take it is P transpose I into P. So this is identity. Also P square into P square transpose equal to P transpose into P transpose. So this is P identity, P transpose, you will get identity. So P square transpose into P square is identity, P square into P square transpose is identity. Therefore, P square is orthogonal. Okay. So therefore, the false statement is 2P. 2P is orthogonal is not true. So option D is the correct one. Next question. Let A be a 9 by 9 real matrix, then rank of adjoint of A is. So these are the options. We have if A is an n by n matrix with the rank of A equal to n, then rank of adjoint of A is also n. If rank of A is n minus 1, then rank of adjoint of A is 1. If rank of A is less than or equal to n minus 2, then rank of adjoint of A is 0. So the possibilities of rank of adjoint of A are 0, 1, n. Here n is equal to 9. Therefore, 0, 1, 9 are the rank of adjoint of A. So option E is the correct one. Next question is about how to check linearly independent and dependent. Okay. So here given vector space is P4 of R, that is of all polynomials of degree less than or equal to 3, which of the following sets is linearly independent? So these are the two set of vectors. So how to check this type of vectors linearly independent? 1 x square x cube is the standard basis for this this set of polynomials of degree less than or equal to 4. So now consider the coefficient of 1 x square x cube of the given set of vectors in the matrix form. So we can write like this. Here 1 minus x minus 2x cube. So I will write this as the coefficient of constant 1, coefficient of x minus 1, coefficient of x square 0, coefficient of x cube is minus 2. So likewise I have written, and after the row transformation I got like this. The given vectors are linearly dependent because it contains one complete 0 row after the elementary row operation. So its rank is less than 4. Therefore, the given set of vectors is linearly dependent. Next, for second set of vectors, the coefficient matrix can be written like this. After the elementary row transformation, I got here rank is 4. Therefore, the given set of vectors are linearly independent. Therefore, the first set of vectors is linearly dependent. Second set of vectors are linearly independent. Hence, option only 2. Option C is correct. Which of the following sets are linearly independent? Only 2. Okay. Option C is correct. If you have any doubt, please give in the comment section. Also, I am not explained this last question deeply. So if you want, please pause the video and see the calculation. Thank you friends. Please share and subscribe the channel.